Hello and welcome to a series of videos which will be on uh, quantum mechanics, Introduction to Quantum Mechanics by David Griffiths. My aim is to just go through the entire book, adding whatever I have as a supplement to the original content in the book, as well as solutions to the problems posed in the book, and we'll just see how we go from there for each chapter. Okay, so we'll start with chapter one. Essentially, the interpretation of the wave function and how that fits into quantum mechanics, and an introduction to the Schrodinger equation. Okay, so the dynamics of a particle of mass m moving, in this case, we're going to be considering contained to a one-dimensional plane, like so. So if we have a particle here, could be a mass or whatever, just moving in a one-dimensional plane with the specified force F of t applied. This can be determined, the dynamics of it can be determined by finding the position of the particle at a certain time t. Okay, so in classical mechanics, this is our goal. We want to find essentially x of t in some terms of a solution, and this is going to be given by, let's say, solving a differential equation, something like that. Okay. Through this, dynamical variables of interest can be obtained. For example, the momentum classically being defined as mass times velocity, or the kinetic energy being a half the mass times velocity squared. Okay, so this ultimately stems from Newton's second law. As you can see, we have by Newton's second law, we have the acceleration written in its differential form, multiplied by the mass, is equal to F, not momentum. It's equal to your force, or force equals ma. Okay. From this, you can even get your momentum relation, which is the derivative. The derivative of momentum is equal to your force. Okay, so the time derivative of momentum, that is. So from that, you can see that if we take the time derivative of this whole thing, we're going to assume that the mass is constant with respect to time, so that derivative doesn't exist. We can say this is equal to the force, and we can just see here, this is our momentum, is equal to the force. There we have mv for momentum, where we've defined the velocity as the time derivative of position. Okay, so specifically, this works for conservative systems, i.e. where the line integral of a force, the closed line integral of work is independent of the path taken, i.e. if we have a closed loop integral of f dot dl, this is defined by work, then this is 0 for conservative systems. Okay, good. So the force can be expressed as a derivative of the potential energy function. So in this case, if this is true, then we can say that F is equal to minus the derivative of the potential with respect to position. Moreover, this also comes written in 3 dimensions, actually. F equals minus the gradient operator of your potential function. Okay, good. So in quantum mechanics, our equation of motion is given by the Schrodinger equation. Okay, so in quantum mechanics, our equation of motion, and we'll put in quotations, of motion, is given by the Schrodinger equation. And the equation has the form as follows. So it's IH bar d psi by dt equals minus h bar squared over 2m d psi squared by dx squared plus v multiplied by psi. And now psi is important. Psi is our wave function. Okay, so this is the whole idea of quantum mechanics, where we have a wave function. Okay, not just any old function, but a wave function. Okay, so as in classical mechanics, given some initial conditions, the Schrodinger equation determines psi of x and t. So we can see here that psi depends on both x and t. The Schrodinger equation determines the solutions, the wave function, for all times t greater than 0. So given initial condition, the Schrodinger equation determines psi of x, psi depending on x and t, for all t greater than 0. Okay, so Schrodinger equation sort of comes from an analogy of electromagnetic waves, but applied to the matter waves by de Broglie. Okay, so with the wave equation, we have solutions which are waves, but because of de Broglie's work, we know that matter has particle wave duality. Okay, so maybe a little heuristic way of looking at this. We can have a little mini version of where this comes from. For equating Planck's quantization of light, so by Planck's quantization of light, we have E equals h bar omega. And Einstein's energy mass relation equals mc squared. We can also write E equals h bar omega as is equivalent to h nu, where this is your frequency instead of angular frequency here, and h bar is not the reduced Planck constant, but where h bar is the reduced Planck constant, and this is just the Planck's constant, standard one. Okay, so if we equate these two, we get h nu equals mc squared, and if we change, well, for weight, for anything with mass, can't really travel at the speed of light. You approach it very closely, but you never actually get there. So instead of c, we're going to change it to some velocity less than c. So we can rewrite this as so: hv over lambda equals mv squared. Well, this is v, sorry. And we've used the standard wave relation v equals f lambda, or nu lambda. So nu and then lambda. So this is your frequency, and this is your wavelength lambda. Okay. So if we divide both sides by lambda, we can rewrite nu as v over lambda. So then this, by cancelling v on both sides, we get h over lambda equals mv. Okay. So from above, we can see that this is very similar to our momentum. And we get p equals h bar over lambda, which is known as the Broglie equation. So the de Broglie equation is just the relation between momentum and wavelength here. Okay. So we're now pertaining to the wave nature of matter, wave nature of particles. Okay, so if we consider a wave propagating in the x direction of the form as follows, psi of x, positive x direction I should specify, equals f of 2 pi x over lambda. This is going to account for some periodicity, meaning that once the wave has travelled lambda in the positive x direction, it's then periodic. Okay, yeah. So if you see, if we substitute lambda in here, they cancel top and bottom, we get f of 2 pi. And for waves after a whole 2 pi oscillation, it has periodicity. Okay. So time dependence of the wave can be given by t as a function of t being given as f of 2 pi nu of t. Okay, and note that the arguments of these functions, they're dimensionless. Okay, we have a dimension over a length over a length, and here we have time over time minus 1. So, you know, frequency is seconds to the minus 1, time is just in seconds. They cancel out. Okay, so the general evolution of the wave can be given by psi of x and t being equal to e to the 2 pi I x over lambda, take away nu t. Okay, and now using the Planck's quantization equals h nu, we can then rewrite this solution as, in terms of energy and momentum, we get the equation equal e to the I px minus et over h bar. Now, there's a lot that's been sort of swept under the rug here, but we got the main thing that's sort of gone is that 2 pi has gone from this reduced Planck's constant, where reduced Planck's constant is just h over 2 pi. Okay, and the reason why we do it is just much nicer. We'd have to write 2 pi everywhere, so it gets rid of that. Okay, good. So, if we now just take the derivatives of this, we get minus I e lambda, not lambda, sorry, psi over h bar. And then we find that I h bar d psi by dt is equal to E times psi. So the energy and momentum in the non-relativistic case are replaced by E equals p squared over 2m and minus h bar squared d squared psi by dx squared is equal to p squared psi. So what we end up with is equating these two. We just get I h bar d psi by dt is equal to minus h bar squared over 2m d squared psi by dx squared. Okay, So we can see that this is for a free particle because we don't actually have the potential. You can see the potential terms are missing over here. So if we have no defined potential, is what we get. But if we do have a defined potential, then energy then reads as follows. We just tack on the V term right there. So if we then postulate that this function f of 2 pi x over lambda can then be generalized to the form with the potential, and also we'll write it like this. If we have this postulate that it can be generalized as so, then we have this form with the potential included. 2m d squared psi of x at t by dx squared plus v of x psi of x and t. There we are. And this is the Schrodinger equation we've just sort of derived. It's not exactly a rigorous derivation, but it sort of gives you a hint of where it comes from. Okay, so the main takeaway is by de Broglie's matter waves and equating Planck's mass, Planck's energy relation and Einstein's energy relation together, you can then use this to derive the Schrodinger equation. Okay, and this is only for conservative forces. If I write this in 3 dimensions, actually it might be more general. So in 3D we have this form. We have IH bar d psi of r and t, where r is now a 3-dimensional vector, and this equals minus h bar squared over 2m with the gradient operator plus v of r, all acting on the wave function here. Okay, so for conservative forces, v only depends on r and is time independent. Okay, so conservative systems also have a constant energy. So by separations of variables, the wave function can be written in this form, which we'll get into later. So I write for conservative v, we get this form of the wave function. Psi of r and t is given by something only depending on r multiplied by this phase factor e to the I et over h bar, where e is our energy, t is time, and h bar is the reduced Planck's constant. So this satisfies the time-independent Schrodinger equation. And if I write the total time-independent Schrodinger equation, you get this form right here. So you can see this is if you were to consider this to be in matrix form, then this is an eigenstate essentially. So this is known as the time-independent Schrodinger equation because there's no time dependency here, it's just spatial dependence. Okay, so that's sort of the introduction to what the wave function is, how it works, and all that stuff. Okay.